Thank you. So my name is Virginie Harcouet-Menou. I work for VITO, that was mentioned in the previous presentation. So it's a Flemish research center located in Belgium. And today I would like to present to you not just one study, but a series of studies that we have performed together with some collaborators, namely the University of Liège and the University of Mons. And all the studies that I will present today have been funded by the SPW, so Service Public de Wallonie. And it's all about harnessing mine water geothermal energy, and it's the case study of the Walloon region. Okay, sorry. So first of all, I would just like to give you a brief overview of the context of the Walloon region. They have set very ambitious objectives regarding renewable heat by 2030. If you look at the graph that I have shown here, so here you see the heat pumps that comes, the renewable heat, sorry, that comes from heat pump in 2022 and the goal for 2030. So it's quite a huge step. But when you look at deep and mine water geothermal energy, it's also a very big step that has to be taken. And especially if you speak about mine water, it's everything that needs to be done because it's 18 gigawatt hour or just the production from deep geothermal projects. So at the moment, there's no production of energy coming from the mines in the Walloon region. When it comes to deep geothermal energy, there were some updates from the legal framework with the entry into force on July 1st last year of the subsurface decree for the development of deep geothermal energy. So this new code is there to ensure responsible and sustainable use of subsurface resources for the present time, but also for future generations. And when we look at really what is the ambition of the region when it comes to mine water geothermal energy, it's really to demonstrate that abandoned mines can support the energy transition for the region by providing sustainable energy and storage solution, and also contribute to the revitalization of post-mining areas. The approach that was taken by the region is a quite logical approach. It's a step-by-step approach. So it started in 2018 with the assessment of the mine water geothermal potential at the regional scale. This was followed by a second step, which was looking into much more detail at what the potential can be, looking at feasibility studies in 3 different coal basins, but I will detail that in the presentation. And the last and final step that is in this step-by-step approach is the launch of the first Walloon mine water pilot project that should start somewhere this year. So first of all, as said, together with UMONS, and we tried to assess the regional potential for mine water to produce and to store heat and cold. So what we did, because a study at the regional scale can be very time consuming and we had a lot of data, so UMONS proposed to use a proxy to understand and to measure somehow the potential at the regional scale. And this proxy was looking at the number of mined coal layers at a given location multiplied by the depth range at which these coal seams were mined. And we did that on a grid every 100 meters. So it was a huge work that was performed, but what is nice is that it really highlights the location where you should have the highest potential for mine water. And based on the conclusion of this first study, and also based on very conservative assumption, the total technical potential in the region was estimated at 1,000, almost 700 gigawatt hour. So this is significant potential, and it was sufficient for the region to justify the development of this energy resource in Wallonia. And as such, SPW Energy decided to launch 3 feasibility studies in the coal basin that I just showed. So in the basin of Charleroi, the Couchant de Mons, and Liège. So that was really the transition from this first step 1 at the regional scale toward much more local assessment. The concept that was looked at in the different feasibility study was always the same. So we always looked at the mine, at a potential reservoir for production, but also for storage of thermal energy. And we wanted to integrate these reservoir and this sort of storage tank into 5th generation district heating and cooling. And the concept was quite simple, and it was using a cold well to target the shallow part of the mine to get cold water, but also to store cold water, and a deeper well targeting this time deeper level of the mine to do exactly the same, but for heat. The methodology that we used for the 3 different studies was also identical. So we started from the potential maps that we had drawn during the first regional scale analysis. We looked and highlighted the high geothermal potential sites. And then this time, not only looking at the subsurface, but also looking at the potential users and looking at the demand at the surface, we tried to find out what could be the best location if there would be a pilot. Once we had selected a site, a given specific site in each of these basins, what was done was a quite time-consuming task, but it was digitalization and georeferencing of mine workings, and then assessment of heat and cold demand on this specific site. And eventually, we looked at potential waste heat in the region. Based on that information and data, we could come up with forecasts of the demand to the reservoir. And what was also important for us was to propose optimal location for the wells. So we did that by using optimization scripts that I will explain a little bit later. And we could run long-term performance modeling to find out what could be the behavior of the reservoir on the long term. We also looked at the costs of the different components of the system to get an economical perspective on the project. So this is just a slide to illustrate what was done. So looking at the potential, we tried to look at high underground potential. We also got some proposition by local actors of the sites that they thought would be interesting for such a project development. Looking at also sites where we could have very different usage, so hospital, administration, residential, and so on. And what was important was also to make sure that it was not only heating demand that we would have, but also cold demand. And looking at a pilot project, it's always better to have a small number of consumer to initially approach. So in the end, for the Liège case, and that's the case that I will present into more detail, the site in the north was the one selected. And here it was just to highlight that based on the data we collected for the demand, we have 2 main consumers. And the hospital that is on the site is one of the main consumers. So as said, one of the first steps after the selection of the site was really the digitalization of the mine works, galleries, and panels so that we could build 1D pipe model representing the galleries and the shafts. And that was used for the modeling of the behavior of the reservoir, but also looking into more details at representing panels and fractured area resulting from the exploitation of the mine. And this type of representation was used as input as well for the modeling. When it comes to finding out the best and optimum location for the wells, so as said, we had optimization scripts defined and especially written for that project. So trying to find out what were the best combination of one shallow well and one deep well to optimize the heat production and cold production, but also the storage of energy. So we came up to series of pairs of well, and looking at also the surface constraint, then we proposed just a few locations for these pairs of wells. This is just to highlight the modeling approach that was used. And here we are looking at the multi-domain model. So it means that we consider the host rock, the galleries, but also the shafts and the fractured areas. So we looked at the demands, so the flow rate that needs to be extracted from the mine. In red, you have the winter season where you produce heat from the mine and then you re-inject cold at the shallowest level, and it's reversed in the summer. Originally, the temperature is around 22 with the deep well that was selected. And you can see that it's pretty constant over time, although you are producing and re-injecting, and it is the same for the cold well. So it means that temperature-wise, it's okay to produce with the scenario that had been defined, and that should fulfill the demand of the consumers that have been identified. We also looked not only at the temperature, but at the variation in hydraulic heads to make sure that in terms of pressure, we would not have any issue. And looking at the results, it means that we would have a maximum of about 30 meters of drawdown at the heating well. So this should be also acceptable. Something interesting as well, and that was assessed, was the CO2 emission and primary energy consumption reduction. Using the system that was proposed, you could achieve up to 72% of CO2 emission reduction and about 45% for the primary energy consumption. So that's quite significant, that's quite substantial. And finally, so here I do not detail all the costs that we estimated, but we looked at the economic overview and what could be the payback time if you would have an investor that would want to invest in such a project. And we looked at two main different scenarios, a scenario where you have no subsidy and a scenario where you would get subsidies. And of course, the subsidy can have quite an impact on the payback time. Looking at the subsidy, we looked at different scenarios where you are a small company, a medium company, because the level of subsidy would be different. So the most important parameters that can affect the project economics are the drilling and the well completion costs, but I think that's more or less the same everywhere, although in some region it's more the network to put in place that would also have some very large costs. The size of the substation used in the 5th generation district and heating cooling grid, and of course the cost of electricity for the heat pumps. And here, so it's just to highlight the conclusion of the Liège case study. So what is important is that when you want to launch such a feasibility study, be aware that digitizing the mine works is the most consuming task, but it is also very critical for the project success, so that you have a good understanding of what your reservoir looks like and what type of targets you can have for your wells, be it existing galleries like what was done in Heerlen, or in some cases it's panels or exploited zones. With proper well location, the mine could deliver and store the sufficient volume at the desired temperature on the long term. And this system can reduce significantly the CO2 emission and primary energy consumption. From an economic standpoint, the impact of subsidies can be significant, and it's mainly because also you need to have quite a lot of investment when it comes to drilling of the wells. In any case, what is important here is that this feasibility study gave some good results and positive results, so the region decided to go on with the idea of a pilot project and the launch of a pilot project. And that's my last slide. I have I have, so I hope I still can present it. So that's the future that should start this year. So there was a call for tender last year. Projects were submitted beginning of the year, and the selection process is ongoing. But it's basically to really unlock and showcase that the concept can work, and to raise awareness and communicate about geothermal energy solution. And with that, I thank you for your attention.